So in the first part of my talk will be devoted to the real-time diagrammatic Monte Carlo. You have seen diagrammatic Monte Carlo in other contexts in the talk of Nikolai and Michel earlier. And I will show you the solution with this method of the out-of-equilibrium quantum dots. And in the last part of my talk, I will present a new technique to compute perturbation theory, which in the case under study yields much faster results. So I will explain that later. So let me first acknowledge my collaborator, especially Corentin Bertrand and Philippe Dumitrescu, who are both here at this conference and present two posters covering what I'm going to discuss and more. And also Serge Florence, in particular for the NRG calculations, and a new collaborator, Bill Trix, a mathematician from Grenoble, who helped us with the quasi-Monte Carlo technique I will describe in the second part of the talk. So, what I'm interested in is our systems which are out of equilibrium with strong correlations. There are many new kind of experiments that we can do in the systems in various contexts, for example, pump probe, or in nanoelectronic with quantum dots, in ultra-cold physics, or in cavity physics. So the challenge for computational physics here, one of the challenges, is to develop exact methods for these systems, for out of equilibrium regime, transient or steady states. And of course, as usual, to have control, speed, and precision. We want to have methods that we can control with some control parameter, compute error bars, and of course, we want them fast. Especially difficult for out of equilibrium problems is the long time behavior. If you make a quench, I mean, solving the short time is one thing, solving the long time behavior, go to the steady states is another, especially because it involves usually resolving various energy and time scales in the problem. So that's the challenge. So the roadmap which we have is to start with simple systems, quantum dots that I will describe today. Because in these systems, we know the physics, we can compare to experiments, and we also have, as you will see, high precision benchmark in equilibrium with Bejan-Zatz. But these methods are not specific to quantum dots. They are quite general and can be generalized to, let's say, GMFT solver out of equilibrium. We have seen in the talk of Martin, we need exact solvers, and there are very few techniques to do that today, but also directly to lattice models for real solids, basically doing out of equilibrium what Michel Ferrero was describing in his talks, or in equilibrium, but for real-time dynamics and transport. So the idea is deceivingly simple in some sense. What we are going to do is to take perturbation theory. So imagine you take a quantity, Q, physical quantity, the function of time, and you expand it in power of the interaction U. You have some terms here, okay? And the point is that I'm going to use perturbation theory with, let's say, 10, 15 orders to find the physics even deep in the strong correlate coupling regime, for example, for the Kondo effect. So we are usually used to think of perturbation theory as being, weak coupling with a few orders. Everything changes when you have a lot of orders and when you can extract physics, in strong coupling regimes, as I will show later. So this is a real-time version, Schwinger-Keldysh version of diagrammatic Monte Carlo, which has been explained before. There are two questions which you need to address. How do you compute this Qn? And then what do you do with the series? So I will take one slide for each of these questions, just to give you the main idea. Then I will show you results and things that you can actually measure. So how do you compute Qn? Well, you open a textbook and you use standard technique out of equilibrium, meaning the Schwinger-Keldysh formalism. In this formalism, that's a bit unfortunate, we can't see the last part, but we have a double contour. You switch on the interaction at some initial time, and then you have, you express Qn as an n-dimensional integral over times, ui, u2. At the end here, under the picture, there is a time where you want actually to do a calculation. And you do that on a double contour with Keldysh indices that tells you on which part of the contour you are. So we have an explicit formula here. In particular, all the Feynman diagrams can be summed here by the sum of determinants, which is the sum of the Keldysh indices of some matrix, which we can write explicitly. The strategy here is to do this sum explicitly, completely. I will discuss that in a second. And to use stochastic method, so Monte Carlo or quasi-Monte Carlo like term, to compute the integral over time. So we know the integral, we just have to compute it. So what's the difference with what was attempted before? The idea is that if you indeed accept to do this sum explicitly, then the long time limit is quite easy to take. And the reason is that function, if you look at it, is in fact centered around the time where you want to compute. So you have to compute an integral at your time t, and your initial time can be very far away. It doesn't matter. The point is that there are massive constellations in this sum, which are deeply related to unitary quantum mechanics, in fact, that you don't want to break and that you do explicitly. So in this version, there is no dynamical sign problem. I mean, the calculation doesn't blow up with time, contrary to previous attempts 10 years ago that were done to do this, that were in fact treating this sum here also stochastically. Of course, the price you have to pay is that you have to compute the sum. So you have an exponential cost at order n to compute the function. But the bottom line is it's worth paying that cost and accepting that cost and using it. So that's the idea. How you compute Qn? Well, you compute this integral by diagrammatic Monte Carlo. Then the second question, and Nikolai has already discussed that in the context of equilibrium, is how do you sum the series? We have a perturbative series for the quantity Q, and the fact is that this series, this function, has a finite radius of convergence in the complex plane of U. Meaning that there is a disk, a weak coupling, where you can just sum the series naively, and everything is fine. But outside that disk, which is determined by singularity, poles, branch cut, which we don't know a priori, I mean, you are in strong coupling, and you cannot sum naively. And of course, the interesting physics is here, around U0 at strong coupling. How do we do that? Well, imagine that there is a region without singularity, the green region here that encloses 0 on the point of interest. We know from a long time in complex analysis that you can find, in fact, a change of variable that will map that into a disk inside the disk of convergence, because there is no singularity here, so there can't be any here. Since the work of Riemann, explicitly Schwarz and Christoffel, I mean, this is well known. We can compute this change of variable. And in that change of variable, because you are within the radius of convergence, your series in the new variable will converge. So we can extract much more information from the perturbative series, even away from the disk of convergence, using this kind of techniques. In some good cases, up to U equal infinity, because with conformal map, infinity can be mapped to finite distance. So this answers the two questions: how you compute the series, how you sum the series. And apart from technical details, which are important, that's the bottom line of the real-time diagrammatic Monte Carlo. Now, I want to show a few results on the quantum dot. So we apply that to a simple model of quantum dot. I don't think I need to explain here the Anderson model for the quantum dot, but let me just flash the notations. I mean, you have a dot here in red with an interaction coupling constant U on site, coupled to two leads, left and right, with a difference of potential, and hybridized using the usual term. And you want to have an exact calculation, let's say on the current, function of voltage going through the dots, or the spectral function of the dots, and you want to see the Kondo effect, as can be seen in experiments. So the first thing when you have a method, of course, is to benchmark it. So first, I want to show that indeed I can capture and describe the Kondo effect in equilibrium. To do that, you compare with a well-established technique, which is numerical renormalization group, or NRG. And you can see here on the left, the spectral function on the dot, in the particle symmetric case, as a function of omega. Gamma is the Fermi-Golden rule without interaction. That's the unit of energy. And U over gamma equal 10, which is already relatively large. We see the appearance even in this technique of the Kondo resonance, which is here. The red curve is the Monte Carlo. The dashed curve is the NRG, and there is very good agreement. This is 0 temperature. Now, this Kondo resonance becomes narrower and narrower. The width of the Kondo resonance, that's the Kondo temperature, which we know here is going to decay exponentially. Here is a calculation of the Kondo temperature as a function of U over gamma, that the red curve here, as you can see, the dots are again NRG points, and you can see that you can capture it up to U over gamma quite large. By the way, if you don't do anything to your series and sum it naively, you will obtain the blue curve, you completely blow away at the radius of convergence at some point. So you really need these techniques I mentioned before. So the point is, we can capture the Kondo effect from our perturbation series with resummation. So that's good. Can we do a little more? Yes, we know since the work of Nozière, in particular in 74, that we have a local Fermi liquid. Can we see the Fermi liquid at low energy? That's another quantity. You typically look at that in the self-energy. Here is the self-energy as a function of omega, real part, imaginary part, in a case which is away from particle symmetry, just to show that we are not limited to particle symmetry. Let's concentrate on the imaginary part here, which is here and zoomed here. Again, we have very good agreement between the two methods, QMC and NRG, and we see that, in fact, M sigma is as omega square as expected. So we can capture the Fermi liquid at low energy. Now, okay, this method would be interesting, but if we were doing only equilibrium, but of course, its real interest is to go out of equilibrium. So what happens when you take a quantum dot and you put a voltage across the dot, like this? Well, you're going to destroy the Kondo resonance because you're injecting energy in the system. You're going to melt the Kondo resonance. And we see that here on the graph on the left, that's the Kondo resonance for different value of the bias voltage. Here is 0 bias voltage. And then you increase bias voltage and you see the destruction of the progressive destruction of the Kondo resonance. We are at 0 temperature here. The Kondo resonance is split into small peaks, if you can call them peaks, and then disappears. Here is the same graph, but on a color plot as a function of omega and u. In other words, the function here is an horizontal slice, if I look at my screen, like this. That would be the left panel. You see the Kondo resonance forming here, narrowing, the two upper bands here, and then the splitting of the Kondo resonance by the voltage at high U for a fixed voltage. That's a finite temperature calculation in that case. So you see the basic effects of the auto equilibrium. Now, the natural question is to ask what is the current voltage characteristics. We can compute the voltage through the dot. So that's the current versus the bias voltage for different value sorry, of U. And you see here, again, the manifestation of the Kondo effect, because if you look at the linear conductivity here at small voltage, you will see that when the interaction increases, it goes asymptotically to this line here, as you can see here in the zoom. And that line here is the unitary limit, the conductance of E square over H. So that's another manifestation of the Kondo effect, again, in an asymmetric case, which we can resolve. Previous methods, about 10 years ago, were able to compute here at high voltage, but having difficulties at low voltage, which we can now reach more easily. Something maybe a little less known, we can, since we are out of equilibrium, compute the distribution function of electron on the dot. So your dot is out of equilibrium, right? Current is flowing through it. Therefore, if you look at the distribution function, you will not get a Fermi function. So the distribution function is given a state of energy omega. How do you populate the state of energy omega? So at zero interaction, we can solve everything. And it's a known fact that this distribution function here is a red curve, meaning we are at zero temperature here. So we have two Fermi functions, two Fermi steps at the two Fermi Cs, separated by the voltage. So you have two jumps corresponding to the two Fermi potential on the left and on the right, which are taken symmetrically here. The question is what happens when you increase U, and when you increase U, you are going to still have jumps. This is U equal gamma over 4, U equal gamma over very large, going to the infinity limit. You will still have a jump and a linear part here. So how to interpret this curve? Well, first, I'm not sure that we can really see that in experiments. I've been discussing that with David Goldhaber-Gordon earlier this week. Not obvious that we can really see that, at least to my knowledge, but whether that it has been measured more precisely. But the point to be made here is that it's not a thermal function. it's not like you have, an effective temperature due to the voltage and you will have a Fermi function with an effective temperature. You would have a different kind of curve. That's not what you get. So that gives you an indication of what kind of effective theories you can do or not do. Fine. So let me now take the last 10 minutes of my talk to talk about the second part, which is a bit more technical development, but recent, which is the quantum quasi-Monte Carlo. So the limitation of the method I have discussed are two things. Well, there is a resummation, okay? But you need also to compute the perturbative orders. And as I mentioned before, the function you need to compute is exponentially hard. So fundamentally, what you have to do, as I said, is to compute an n-dimensional integral, which that's a formula I wrote before as a function of the times from initial time, and you have this function. And the point is that the function costs you O2 to the n, in fact, n cubed to the n, to compute. So how are you going to integrate that in large dimension? And you would like to do that with a minimum number of evaluation, because 2 to the 10, 2 to the 50, that become to be a serious number. So how do we do that? How do we do integration in large dimensions? The conventional wisdom, I would say in our field, or at least for me before I worked on that, was the following. For small dimension, so n here is at an axis of the dimension of the integral, number of the orders. For small dimension, we can certainly use quadrature techniques. And if we look at the error that you make by computing your integrals, the only point is how that thing is going to converge with an n, meaning the number of points that you evaluate the functions. So typically, you will evaluate your function on something like given on points. And the question is how the error goes with n. With quadrature, you can make it exponentially. But if the dimension becomes bigger than, one can discuss, but 3, 4, 5, typically we say, okay, we can't do that anymore. It explodes exponentially. And we use stochastic techniques, Monte Carlo. And the errors in Monte Carlo will scale like 1 over square root of n, which is a very flexible method. That's what we used before. But 1 over square root of n is slow. So can we do better? And the fact is that there is an entire field in mathematics which deals with intermediate dimensions, not 10,000, not 3, and these are quasi-Monte Carlos. So in these methods, under certain conditions, you can have a scaling of the error being of order 1 over n, which is much faster. Now, of course, this comes with conditions, and I will discuss that in a second. And this has been shown to work up dimension of a couple of hundred. So when we are doing perturbation theory here, because we have the 2 to the n anyway, we're not going to compute much more than 10, 15. So even if you take a lattice, you will be below that limit. So it's interesting to see whether these methods could be used. So that's what we tried in this very specific problem. So let me tell you a little bit what quasi-Monte Carlo is, because not everyone may be familiar with it. In order to do this integral, you will evaluate the function of some special points, which are called low discrepancy sequence. Typically, we use a Sobol sequence. And the idea is that you're going to approximate the integral by the sum over this point here. And under good condition, which I am not going to describe here, it will take too long, if the function is smooth enough, meaning in the proper functional space, then you know that the error of your integral is going to scale like 1 over n plus corrections. That bound may not be optimal, even mathematically. In practice, if everything goes well, you will get 1 over n. This is a picture of these points. The Sobol points, they are absolutely not random. They are regular or quasi-crystal, in fact, in the hypercube in dimension n. This is a representation in dimension 2 to compare with random numbers taken from a Mersenne twister. As you can see, this is very different. Random numbers would put clusters of points and have empty regions. This is clearly different. So the name is deceiving you. I mean, quasi-Monte Carlo is absolutely not Monte Carlo. There is no random number. The way you manipulate it, the way you compute error is vastly different. But that's a name in the mathematical community, so we have to deal with it. And of course, they call that QMC in order to maximize misunderstanding with us, but that's how it is. We have to accept it. The point is the function we are going to integrate, this Fn, is it smooth enough? And the answer is no. If you try it just directly, it won't work. No, but there is a way to make it work. And the way to make it work, to use the language of collaborators, is to warp the integral. So this is a fancy term, but it just means find the change of variable u of x in n dimension, where x is on the hypercube, 0, 1. So that's just this function, just a change of variable, right? Plus the Jacobian. And the goal is to make the change, the goal of this change of variable is to make the function smooth, flat, and to enter the hypothesis of the theorem. So what we do is to build this change of variable. It's a complicated n-dimensional function. Yes, thank you. You are going to do that with a model function of the function fn you want to compute. So you are going to take a model function Pn. I will come back to that in a second. And from that function Pn, we are going to construct u of x. Formulas are in the paper, such that the Jacobian is 1 over Pn times constant. So if you use now the quasi-Monte Carlo in the new variable, you will see that you have a sum of fn over Pn, because that's a Jacobian. In other words, this model function accomplishes two things. First, it's a reweighting function, similar to reweighting function in Monte Carlo in some sense. And the second, it gives you the change of variable, u of x, that's going to deform the point to adapt it to the function that you already want to integrate. If your function is flat, you put less points. If you put function is sharp, you put more points. So you redress your function by changing coordinates. If your model function was perfect, if Pn was Fn, you would sum 1, you would in only 1 point. Of course, the constraint is you can't do that because you need to have a model function which has some structure that allows you to construct the change of variable and operate the calculation. Now, which kind of model function do we use? The model function is an approximation of the integrand in n dimension. And there is a notion that this function should be optimized for quicker convergence. So it's a kind of machine learning problem if you want. So a large class of function that we could use to make this change of variable is written here. It's a product of function of the time differences, maybe with tensor indices here with different kind of functions. And these functions are well known in machine learning context. They are called functional tensor train. They are from MPS techniques. So that's general, but what I'm going to use today is this very simplest case, even without any optimization. I'm going to take a simple product of functions of different of times, and even I'm not going to optimize on that function. I'm going to take a simple exponential with one number. And that is already sufficient to have a good result. And of course, we can try to improve it by optimizing. We show a little bit in the paper. I will not discuss it here. So if we do that, let's compute the integral of the quantum problem. You compute the 8th order perturbation theory of the dot occupation in equilibrium divided by the exact solution given by Better and Zatz as a function of the number of sampling points. The previous real-time diagrammatic Monte Carlo, that's a black curve as a function of n. So we will go to 1 because it's correct. We'll use the correct answer. And the red one is the quantum quasi-Monte Carlo, the quasi-Monte Carlo calculation of the integrals here. That will converge faster. Note here that this is a log scale. So you will, in fact, converge faster. So to see the convergence rate, I will subtract 1 and take the log. So I'm going to replot the same curve in log. So that's the same curve, but in log space. Log. So the black curve, as we see, decays like 1 over square root of n, as expected here. The envelope, that's Monte Carlo. But the quasi-Monte Carlo decays here, and that line here is 1 over n. You see that for some decades, it's almost 1 over n, and then slightly deviates to close to 1 over 8 in our calculation. So you see for 100 million points, we have 4 order of magnitude difference in the error because we have a different scaling. Now, using the change of variable is crucial. If you don't do it, as I said before, you will obtain the blue curve, which is bad. It doesn't work very well. You can also choose the change of variable and do Monte Carlo. It will improve the Monte Carlo. That's the green curve, but that's still 1 over square root of n. And it's a combination of these two, the model function and the quasi-Monte Carlo, that give you the best and most fast conversion method. So you need these two pieces together in order for this technique to work. Now, the natural question is how long in orders can we continue that? At some point, the function becomes so long to compute that we cannot do it. But here it's order 12. You can see that even at that's order 8, that's what I showed before, order 4, and order 12, you can still follow more or less 1 over n. which means that at order 12, that's the exact expression that Philippe derived from the Bethe ansatz, which is not very nice looking, but I mean, it's exact. And numerically, here with about 10 million points, you get 5 digits for these kind of things. We can even go higher, but then we are hit by machine precisions in the calculations. Just to flash one result, why is it important to have methods that are faster? It's very important even for impurity solvers, because in many problems, we want to do parametric runs. We want to run many calculations for different values of the parameters. This is an example, again, in the quantum dot. That's the so-called Coulomb diamond at 0 temperature. So as a function of epsilon d, the gate voltage and the current, there is a whole region here in white, which is forbidden by Coulomb blockade, in the middle of which the Kondo resonance will appear as a ridge, and the name Kondo ridge, which you can see here in some experiments. And here we are able to do calculations sweeping in epsilon d at different values of u along these lines. So if you really want to see that and compare to experiments, I mean, you need it's great to have methods that are faster. For example, one point here in this graph is about 25 hours CPU times, while it was several thousand or 10,000 before. So for this problem, I would say that we have been successful. And I come to my conclusion. I've discussed the solution of our Coulomb quantum dot. I discussed the fact that we use perturbation theory even at strong coupling. This attempt to use the quasi-Monte Carlo, which in this problem here was successful. Of course, now we need to try it on other problems and learn when it works, when it doesn't work, in imaginary time, in lattice problems. And the roadmap I already said before, I mean, we want to go progressively to lattice problems. And on that, I will thank you for your attention.
Before we go to the questions, I want to make an announcement that there's no change as far as the banquet schedule that will proceed as planned in the Meadows at 8 o'clock tonight. And with that news, then I can open the session for discussion. First questions, yeah, Christian?
Good work. I'm wondering, why is this function that you come up with, this super product function, with this exponent that you showed, so great for so close to your real function? Because when we were doing the Monte Carlo, we also did a weight function, and we tried to first construct it from just the product function over the major dimensions. And then we try to do all possible convolutions in addition to the product. And even that has very small overlap. And we supposedly determine these functions, and they tend to have very small overlap when dimension grows. So small and small overlap.
Yeah. Yeah. So
you're going to have to repeat the question.
Yeah, that was a long question. I mean, the question was basically what makes a model function works, and then the question described his attempt to do it in imaginary time. The point, I think there are several points which are necessary. One, you need to take the difference of times. If you don't, it doesn't. And the real reason here is that if you look at the function, it will capture basically the asymptotics of the function, the tail of the functions, quite well in that problem, because that's Keldysh. And if you think about a function, which you have the core of the function and then the tail of the function, you need to integrate. In larger and larger dimension, the volume of the tail is going to be basically of order 1 in relative terms, because in large dimension, volumes are either 0 or 1. They grow exponentially. So I think that's the reason. It fits very well the tails and the asymptotic of the function. So that's probably the reason. And if you change the tau, then if you take it wrong, the method degrades for exactly that reason. Then we show that there is a technique to make it robust against these changes by projecting again and optimizing the function.
Yeah,
I guess I have a very related question. So,
why don't you go and
yeah.
If the question is long, then you fit into the.
Sure.
Yeah, so I guess I have a very related question. We have a lot of determinant functions, etc., in variational Monte Carlo.
can this method be applicable for such situations, for sampling such probability distributions?
Okay.
Calculating such a thing.
It's always difficult to say no in such a thing because you are recorded. But I don't think so, because your dimension is going to be much higher. It depends on your dimensions. It really depends on your dimension and whether you can flatten the function you integrate. That's the correct answer.
So this n is the number of electrons.
That's a number of times. That's a perturbation order. Yeah. So that's the dimension of the integral.
Yeah, but in variation quantities, you can do hundreds of electrons. If I have 100 electrons.
There are problems of 100 dimensions where this method works. It doesn't guarantee that it will work. And I think it would be interesting to try. You have to try. It is known in some problem in finance, for example, that you can get it work to 200-300.
Yeah,
but
the question I had is there some work on what model functions would work for representing determinants?
Not that I know of.
Okay.
We just tried and then.
Other questions? I have a question. You showed your beautiful distribution function. You show your beautiful distribution function in the dot with that jump, and there was a lot of work in the past. People trying to guess what the distribution function is.
Yeah.
Can you comment? Can you comment on what's the physics of that distribution function?
Well, I think it's difficult to interpret really, but to comment on the old work, there's approximated work within CA, which find qualitatively the same thing. Okay. So it's compatible. Now after that, still at 0 temperature, you still have the remnant of the jump of the Fermi functions. Now, the linear part close to low energy, I don't know. You can define locally a temperature if you want at very low energy, but
it's not the sum of two Fermi functions.
Not that we know that.
Okay. So, any further questions?
Maybe there is questions on the Zoom.
No questions.
Oh.
Okay, if not, let's thank Olivier for a very nice talk.